Hello and welcome to video lesson 21 on failure theories. Our learning objectives are to be able to state and apply the following failure theories. Maximum shear stress, which is also called the Tresca criterion. Maximum distortion energy, which is also called the von Mises criteria. And the maximum normal stress criteria, which is called the Rankine criteria. For this section, I want you to read Beer and Johnston section 7.5. However, my presentation of this material is going to vary a little bit from the presentation in Beer and Johnston. Beer and Johnston typically are concerned with plane stress problems. However, the things that I'm going to give to you are more general than the way it's presented in Beer and Johnston. And the way this is presented is more useful for instance, when you're working with 3D models and SolidWorks or things of that nature. But if we understand that for plane stress, at least one of the principal stresses is zero, then these equations are easy to apply in that case as well. So my presentation is going to vary a little bit from Beer and Johnston. And I just want you to be aware of that. So principal stresses, there are always three of them. Sigma 1, Sigma 2, and Sigma 3. And for plane stress, at least one of the principal stresses is zero. So one is always going to be zero. You could have others, but the other two that we're going to get are going to be Sigma P1 and Sigma P2 from Moore's circle. We just order them Sigma 1, Sigma 2, and Sigma 3, where Sigma 1 is the most tensile stress, Sigma 2 is between Sigma 1 and Sigma 3, and Sigma 3 would be the most compressive of the three stresses. That's a common, consistent convention. So let's just introduce the failure criteria. We just have three distinct tests for failure. We have two that are very similar, used for similar applications. And for ductile materials, we would use the Tresca and von Mises criteria fairly regularly. The von Mises is a little more lax than the Tresca criterion, so it's possible you could have failure by von Mises, but not, failure by Tresca and not by von Mises. You can still have a measure of safety with the von Mises criterion. It's just two different understandings of what two scientists believe to have happened in to happen in materials as they fail. So as we have Tresca and von Mises, we have two formulas here that we would use with ductile materials. Tresca is more strict. However, von Mises has to do more with distortion energy. So a lot of individuals would use the von Mises criterion. You would want to check with whatever codes or design standards you're working with as to what you would want to apply for your particular application, or use good engineering judgment with whatever problem you're working with. So for failure criteria, so for our failures not to happen, with the Tresca criterion, we're taking a look at the absolute value of the difference in Sigma 1 and Sigma 3 and comparing it with Fy. So if the absolute value of the difference in Sigma 1 and Sigma 3 is less than Fy, we assume that we're safe. If it's greater than, we assume we're failing. We're at a point of failure, and if we are right on the line, we probably either okay if we're working with an appropriate factor of safety. So von Mises is a different formula. It's Sigma 1 minus Sigma 2 quantity squared plus Sigma 1 minus Sigma 3 quantity squared plus Sigma 2 minus Sigma 3 quantity squared all over 2, and take the square root of everything on this side. This will actually give you something in units of stress, and we would compare that with the yield stress. So this term is also sometimes called the von Mises stress. And then the Rankine criteria is based on the maximum normal stress. And we would compare that with the tensile and compressive strengths of the material that we're working with. So we would be interested in our maximum tensile stress or most tensile stress. And if that is less than the ultimate strength, then we would have safety as far as tension goes. If we have the magnitude of sigma 3 and it's less than the compressive strength for compression, then we would have safety with regard to compression. In other words, we'd have to have a case where we had tension and a case where we actually had sigma 3 in compression. So I'll just put that note here. Sigma 3 must be compressive for this to be a failure mode. So if sigma 3 is in tension, we would ignore this. If sigma 3 is in compression, we would consider that limit state case. Let's take a look at an example. And I've got a plane stress element. It's at a critical point in machine bracket made of steel. It's shown. We know that the yield stress is 36 KSI. And we want to determine if failure occurs using the Tresca criterion, the Moore-Coulomb criterion, and the Rankine criterion. And for the Rankine criterion, we're going to assume equal strength and compression and tension, and that's 36 KSI. So we're going to assume in both of those cases that the material is 36 KSI strong. Well, if I wanted to deal with this problem, I would want to work with Moore's circle. So for my element, I have sigma x of 20 KSI and tau xy of 18 KSI. Of course, on the original element, this is positive 18. But for drawing Moore's circle for the x point, this is negative 18. So what I would want to do in constructing Moore's circle is I would want to find the point 20, negative 18. And then I would want to find the other point on Moore's circle that gives me the diameter. So I would come back over here. I've got 10 KSI. So that is negative 10 because it's compressive. And then I've got 18 KSI that is spinning clockwise, and that's positive for that point. So for this point, I have negative 10 and 18 for sigma y and tau xy. And then I have for sigma x and negative tau xy, 20 and negative 18 for the other points. I need to connect the two. So sigma average is 5, 0. So it's an average stress of 5 KSI. Well, if I was to take a look at my right triangle here, I would have 15 on this side. I would have 18 on this side. And the radius is the square root of 15 squared plus 18 squared, or 23.4 KSI. So I can get my principal stresses for the state of plane stress by adding the radius and subtracting the radius from the average stress. So that gives me sigma 1, the most tensile, of 28.4 KSI, sigma 2 as 0, and sigma 3 as negative 18.4 KSI. So I have sigma 1, sigma 2, and sigma 3 identified. So let's examine the three failure criteria. So Tresca is sigma 1 minus sigma 3. That's 28.4 minus a negative 14.8. So that gives me a stress of 46.8 KSI. I would compare that with the yield stress of 36 KSI, and that is a failure of the bracket. The Tresca criterion says the bracket is going to fail. So von Mises, if I check that criterion, I'd want to calculate the von Mises stress as the square root of sigma 1 minus sigma 2 quantity squared plus sigma 1 minus sigma 3 quantity squared plus sigma 2 minus sigma 3 quantity squared, all divided by 2. So when I plug in the numbers, I end up with a stress of 40.83 KSI, which is greater than 36 KSI, so that is also a failure. However, if I take a look at the Rankine criterion, I'd notice that sigma 1 was tensile and sigma 3 was compressive. So if I was comparing each of these stresses with a criterion of 36 KSI, both of them are less than 36 KSI, and I would predict that the element is going to be safe by the Rankine criterion. Now, should I be doing this with a steel bracket? Probably not. I should be taking a look at the Tresca and the von Mises criteria that would say that the bracket is going to fail because those are more reasonable and accurate models for yield surfaces for ductile materials like steel. So that's all for video lesson 21. Thanks for watching.